Assalamualaikum and a good day. Today, me and my friends are going to present about probability distribution used in finance. So we're gonna have two parts, that is discrete and continuous. These models are essential for understanding risk and return in financial market. So we're gonna start with Bernoulli distribution. The Bernoulli distribution represents an event that has two possible outcomes. A random variable x follows a Bernoulli distribution with parameter p if it takes the value 1 with probability p and 0 with probability 1 minus p. So, the expected value for ex is p and the variant of x is p in bracket 1 minus p. Now, let's move on to the binomial distribution. Imagine we have n independent trials, each with a probability p of success. So, it gives us the probability of having k successes out of n trials. So, the probability formula is shown on the black box. And the expected value for the binomial distribution is ex equals to np, and the variant is variant x equals to np in bracket 1 minus p. Next, we're gonna discuss the Poisson distribution. We might use a Poisson distribution in finance to model the number of rare events occurring in a fixed interval of time or space, like the number of trades in a financial market. And the probability formula we can see in the white box, where lambda is the average rate of occurrence. And the expected value is ex equals to lambda. Also, the variance is variance x equals to lambda. To summarize, we've covered the Bernoulli binomial Poisson distributions, which are fundamental in financial modeling for discrete events and outcomes.
Continuous distribution. A continuous distribution is one in which data can take any value within a specific range, which may be infinite. Continuous has three types, which is uniform distribution, Gaussian, normal distribution, and log normal distribution. Uniform distribution is a model, a situation where all outcomes in a range are equally likely. Uniform distribution on the interval AB, A less than B. For example, rolling a fair die. Next, Gaussian normal distribution is a model, a distribution of where most of the value cluster around the mean. The parameter is mean and standard deviation. For example, height of people in population. For log model is a model distribution of a variable whose logarithm is normally distributed. Parameter is mean of log, standard deviation of log, ln as nm2. Example, distribution of income. Next, comparison between discrete and continuous distribution. For discrete distribution, outcomes are accountable and often integer, while continuous distribution outcomes are uncountable and can take any value within a range. Discrete distribution is used when dealing with counts or events that occur in discrete steps, while continuous distribution is used when dealing with measurement or quantities that can go very smoothly. For discrete probability mass function, PMFS typically bar chart, while continuous probability density function, PDF, as typically smooth curve.
Assalamualaikum warahmatullahi wabarakatuh. Today, I will talk about chapter 2. Firstly, problem statements. Financial returns often exhibit characteristics that are not well modeled by traditional Gaussian distributions. These include heavy tails and sweetness, which can be captured by stable distributions. Stable distribution can be either continuous or discrete. In this content, we focus on modeling financial returns using discrete stable distributions, which can better handle extreme value and provide a more accurate representation of financial data. Secondly, real financial problem. The modeling of intraday returns of bond future price using discrete stable distribution. Option price. Model often assume normally distribution returns, which can underestimate the likelihood of extreme movement in the underlying asset. Example application. Pricing option on asset with return that as habitat, improving the accurate offerings natural valuation.
Now, I'm going to explain about the solution of this problem. First, we gather the required information, which is the parameters. We assume the parameters where the current stock price is $100, the strike price is $105, the time to expiration is 1 year, the risk-free interest rate is 5%, which is 0.05, and the volatility of the underlying stock is 20%, which is 0.20. That was step 1. For step 2, we calculate the D1 with the formula given below. Once we obtain the D1, which is negative 0.2244, we calculate the D2 with the formula given below as well, which is negative 0.2244. We obtain 4 main points from the article. First is the discrete stable distribution. The paper introduces discrete stable distributions as a solution to model financial returns that exhibit heavy tails and follow a discrete nature. The second point is parameter estimation. The article focuses on methods to estimate the parameters of these discrete stable distributions from real financial data. The third point is comparison with other methods. It compares the performance of discrete stable distributions with normal and continuous stable distributions in fitting real market data. The last one is the estimation method. The empirical characteristic function method ECF and the approximate maximum likelihood method ANL are discussed as viable methods for parameter estimation. We obtain 4 main points from the article. First is the discrete stable distribution. The paper introduces discrete stable distributions as a solution to model financial returns that exhibit heavy tails and follow a discrete nature. The second point is parameter estimation. The article focuses on methods to estimate the parameters of these discrete stable distributions from real financial data. The third point is comparison with other methods. It compares the performance of discrete stable distributions with normal and continuous stable distributions in fitting real market data. The last one is the estimation method. The empirical characteristic function method ECF and the approximate maximum likelihood method ANL are discussed as viable methods for parameter estimation.
Hi, I'm Vidya Gunasekharan. To conclude, this chapter provides a comprehensive overview of commonly used probability distribution in financial models, focusing on both discrete and continuous types. Discrete distribution include Bernoulli. Models binary outcomes with expectation EX equals P and variance sigma squared of X equals P times 1 minus P. Binomial extends Bernoulli to multiple periods with expectation EX equals NP and variance sigma squared of X equals NP times 1 minus P. Poisson models event occurrence over a fixed interval with both expectation and variance equal to lambda. Continuous distribution include uniform. Model equals likely outcomes within a range with expectation EX equals a plus B over 2 and a variance sigma squared of X equals B minus A squared over 12 Gaussian, also known as normal distribution. Models data clustering around a mean with expectation EX equals mu and variance sigma squared of X equals sigma squared. Log normal used for variables whose logarithms are normally distributed with a complex expectation and variance formulas involving mu,